Okay. Probably not loud enough. I have to go right up to my face. Yeah, that's the way. So, ooh, a little loud. Don't know. I'll have to check myself what the stream is like. Should be fine. And to what extent am I going to be trimming stuff off the end? It says I'm alive. Crazy days. Alright. Well, that's easy. So, what's going on this morning? Weird time to stream, but whatever. I had intended to do, and I probably still will do, a couple of things about some little utilities for reading tabular data. But just for like 15 minutes while I'd started doing this and it's on my mind, and just to try out the streaming stuff, in the orchard, Connor, who's been looking at APL stuff recently, asks about minimal artificial life, which is some YouTube video. Someone who quickly codes up a quick canvas, HTML canvas renderer with and generating some particles and doing a whole little simplistic physics simulation. Now, I've only watched up to sort of changing the parameters of the interactions. But I did something like this sort of once upon a time with my physics simulation thing, so I thought it'd be fun to go back and I'll just have a little go at this and see how far I could get. So to start with, I wanted to get some of the like grubby boilerplate out of the way, which is not much in APL, but in order to render this, I'm going to use an HTML renderer. This thing could probably easily be extended to some kind of web service thing, or a single page Jarvis app or something, which might be an idea to do in the future. But to start with, I'm looking at APL, which is a cool little, I think this is actually, having looked at the code, I think this is a table, or one of these is a table. Just gets filled with colors and you can decide how to, it's like a pixel editor written in APL, so you can, well, written in APL but rendered using JavaScript and communicating via WebSockets back and forth. Now, I don't actually need the WebSocket communication part, but it was kind of useful just to get myself in the headspace of what to look at. So, yeah, so we're basically just copying this little particle sim, but we're going to do the computation in APL, and we're just going to render using HTML and JavaScript. So, this is a pixel. Yeah, I'm going to get rid of that because I don't actually need it. Good enough. So where I'm up to is I have a function which initializes an HTML renderer object. It has this WebSocket receive event, but I don't actually need that at all. So I think I'll just comment out for now and show dev tools, because I was confused about rendering, or I was confused about fill rect, fill style. What's a function? What do you assign to? Blah blah blah. So what it is like this. I've got a single HTML file that just puts the HTML5 canvas up, and then there's a little script. Again, don't really need these functions right now. We just get the 2D context of the canvas to draw on, and we have a draw function that draws rectangles. So that's basically all the boilerplate there. Then we run our init function, create a new HTML renderer thingy. There it is. There was a way, wasn't there? Pin it on top. Windows 10 pin window on top. I used to have a little applet for this, but then click the desk pins icon. Do I still have desk pins? No, isn't there? I found out there's an inbuilt or should be asking people questions. There was some kind of thing. It's not turbo. Ugh. Somewhere in here's a thing that lets you do lots of cool Windows things. I forget what it's called because once you install it, you kind of stop thinking about it. And I used to have that pin thing. Sway stream sticking out scan. RDP. Problem is I don't know what I'm looking for because I've entirely forgotten what it's called. Those 10 extensions. Extended behavior. What is that thing called? La 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 la. It's not recorded of that. Nah. You know what, doesn't matter. We don't need this. We can just stick it over here. Deal with stuff. Okay. Right, anyway, it's gonna move. This position goes there. Ooh, maybe we can, that might make my life easier. 0, 100. Where are you? Or if I manually move it, do I get the position? Yeah. Oh, I don't even know where it's gone. Alright. If I do that, and I do that, and then I get... Yes. Brilliant. So we're going to get the position and size that puts it over there. And you know, one day, right, and we can show the dev tools, but that won't be that interesting right now. So I've got an HTML renderer. 9 life. Create a new namespace called life. This is going to be like the container that has all the defaults for creating a collection of particles and stuff. and it will also, I guess, contain the update function, which is to take the HTML renderer, execute JavaScript, which is an HTML renderer method, some JavaScript, which will be the draw function from our app. Then the information, which is X and Y coordinates, color, yeah. That's the easiest way. I'm going to send it a list. And it's going to draw multiple. Maybe we'll put the each inside here. So say this takes a matrix. Yeah, well, we'll try it anyway. So let's say our particles are, and it's a 500 by 500 canvas. Thinking what's the most elegant way, but I'm not going to think too hard. Like, those are some random positions. And what you can do no, because draw is going to take the list as a thing of parameters, so we're not actually going to want to quad JSON it. I think it has to be, we have HR, execute JavaScript, it's going to be draw 10, 10, a color, and 5 I think is the size, and there's a dot, and we basically want to create a big string of draw calls, as many as there are particles. So if our color is black and our size is 5, I guess we'll keep it numeric in the APL side, then it's draw open, comma, format each P. Ooh, oh yeah. Draw dot. Yep. Not quite. Oh, yeah. Each row. And the commas. What's the easiest way to get the commas? Oh man, I'm looking at a great here. We could do the join thing. Ugh, it's ugly, isn't it? Array notation might sort this out, I wonder. That'd be an interesting thing to look at. Let's try and make it first. So you do want this concatenated with each. And then for each of those, we also want a comma, the word black, comma, and a 5, close parens. There we go. That's an ugly way to do it. And the particles are just gonna have positions for now, and we'll figure out how to extend it to colors, or make it more nice and general later. So it's our draw. Can you do it with a jar? Yeah, okay. Draw, concatenate, so we don't need all this enclosing a scalar. Let's fill this up because we don't know yet. Draw each joining. I mean, what happens if you quad JSON rank 1? It's all the same, isn't it? Omega. Format each. Comma. Let's catenate each with the color, which again we'll supply later. It's tempting to make it dyadic, but there's enough parameters that like I don't even know if I want to give it the same syntax as it has in JavaScript. That would kind of make sense to sort of marry them up. Already? I'm missing a comma. Okay. So we can draw our particles and then we have this list, but we actually want same again. So really it's a join function, which is left tack. Yeah. Left tack, comma, alpha, comma, right tack slash omega. And then we can comma join this, and we can semicolon join the instructions at the end. And probably pick that out. Okay. So there's our JavaScript, and then if we look at this, we can hr.execute JavaScript life.draw p, and there's a bunch of particles. So run is a loop. If we quit, if we set quit, let's quit. Otherwise, it's the particles compute. So this is really an abuse of def, and if I do it this way, The run loop should be trad font. If q return and do compute forces or something. We'll call it interact. So every step. Oh yeah, sorry. While we're not quitting, let's do that. I'll put in a new thread. I don't think this will work. How did I do it? Oh, yeah, okay. Yeah. Well, run minus gets 1. We'll do it with steps, sadly, because so it'll be a limited number of steps rather than an infinite loop, because I can't think, and I'm sure I'm going to mess it up if I try to run an infinite loop in one thread and then have like a quit flag, but I don't know how to set the quit flag in the running thread. You know? So I'll have to ask someone about that or find out about that. Then we update. Well, this is update, isn't it? We just draw them. That's the 2 steps. The particles interact and then they're drawn, and interact and then they're drawn. So initializing is to say that the particles are number of particles, the color, and the size, and it's the number of particles to reshape the canvas size, which should be passed as options later, but we know it's 500 for now. Then care about the color? Oh yeah, okay, we'll just draw them. Draw. Yeah. Okay, well, we're fixed for now. Ooh. Oh. Had one called life. Expunge. Go to. Oh, we're in it. And a life. Interesting. Ah. That should add it. Good. Okay. No contradiction no more. Alright. Oh, it just returns it. Where's my HTML renderer? Here. So draw's actually going to do the thing. Okay, and start. We plonk the HTML renderer above. Let's keep JavaScript JS or inside the live sim. Makes more sense. Keep everything local, maybe. Don't know what this returns though. And then we can return the JavaScript, or we'll return the response. I don't know. HR, yeah, exactly. Oh, so you're gonna do everything. Because I already have an init function. Creates the HTML renderer. For now, they're kind of interlinked, aren't they? This is ugly. Oh. So I think the arrangement of everything is really ugly right now. But we're getting there. Really, I want like the rendering stuff in one namespace. I want the simulation stuff in another namespace. That was kind of the idea. And then we'll run, and it will just be one simulation. But like in the spirit of the example that I'm copying from, I guess it makes sense to have everything kind of together for now, and it can be split apart later. So life.read gets read add life.read. Give me 10. Really? Yeah, we don't need dev tools no more. Okay. So init 10, 100 steps. Need our interaction function, which takes a set of particles. And then, yeah, the first force it does is like a gravity. Gravity is well, it is equal to minus GMM on R squared in normal parlance. So F gets minus G, and you have to do M dot times, you have to need the mass of every particle and the mass of every other particle, and 1 on the distance squared. Or I guess, yeah, right, it makes divided by the distance squared. And for the sake of like making it look like a kind of fraction, I'm going to parenthesize the end even though I don't need to, the R squared. And so R is, we have, what? Am I not? Oh yeah, okay. In this function, we have a bunch of positions, and we want to find the relative distances, and that's actually R in this case an absolute value, and it's an outer product, so you can actually express this as jot minus selfie split, but that's relatively inefficient. Well, it's inefficient in so much as in APL it's using nested arrays, and what you really want is subtract minus rank 199 selfie, which is the same data, just all flat, so it's much faster to compute this way. It's still incredibly wasteful, but it's the same nested for loop as the original example, and the rest of computational physics, or at least for matter simulations, is largely just seeing how you can keep the sort of physical properties of an ensemble while just cutting down the sheer number of computations as much as possible. And in my Apple Fizz thing, I think I got away with that to an extent by you basically that's rescaling the verlet, I think. LG cut optimized here. Yeah, you have like a cutoff distance outside of which you don't bother computing because you've reached the or you're estimating that you've reached the limit where the interaction is negligible, so you don't have to compute the distances between all of the things, and then every so many steps you compute, you know, the cutoffs, or which particles have come within cutoff of each other, and use key to sort of group together which particles should be interacting with which. So anyway, so here we're like massively over computing, and it's also true if you look at the shape of this, it's a 10 by 10 by 2, and I'm pretty sure we only need the leading one of the triangles of the outer product, as it were. As in, what you're computing is a force. Oh yeah, so you also need the absolute distance, which is the square root of the sum of the squares. So that's the magnitude there. Okay, so this is every particle for each particle. And alright, it's mag of that, and mag is square root of the sum of squares. Then just bottom triangle. No, you have to sum up the force for each thing. Yeah, that's right, isn't it? So we use this table to compute the forces, and then we sum up the forces. The forces will have a direction. Ah, that's the annoying thing. Yep, I remember now. It's apple cart it maybe. I think I'll only do this for 15 minutes, and then I might come back to it another time, because there's some other utilities that I think are more useful to have out soon, that I think I want to put out. Or we'll see. Direction. No, it's just the opposite of the direction. So I mean, you could try and use complex numbers since we're in 2D, but anyway, the direction is basically just normalizing these. And that is to take them and divide by the magnitude. So these are like the directions, and I think we should be able to tell if we take the magnitudes of these, it should be 1. Yeah, exactly. So that's what the direction of each of the vectors are. It's just normalizing the vectors. So the direction D And even though I wrote like this because it's quicker, I actually prefer to parenthesize my use of the rank operator when I've got it in the actual code. So it's dividing each vector for each magnitude scalar. To normalize, have the directions. Then we're going to have our force. So the masses are just going to be 1. And G is a constant, which is like negative 9.81. We'll probably tweak that. Set it to 1 for now. And we're saying they all have the same mass of 1 because we haven't put mass in as a parameter. So really we're just going to get a table of our distances. And yeah, okay, for now it's just going to be 1 over r squared. Oh. Yeah. We could set quad div and ignore. Yeah, don't like that. Localize it. And oh no, because you want jot dot less than selfie. All those, yep. Bottom left. I think these are the forces. The force is mass times acceleration, so the acceleration is force divided by mass. We're calling the mass is 1, so it'll just be the force. D times rank 1 naught again. Acceleration, they have a velocity. So your position becomes position plus velocity. Velocity becomes velocity plus your acceleration, which is the force for that time step. Let's really check how they're doing it.
Another rule to make the of particles. Finally, currently
Oh yeah, and this is their reaction code, huh? They find the distance, they're doing the geometry r squared. Acceleration is added to by the force. Yep. Oh, the particles have these properties, AX. And their velocities, alright. I don't want to make each particle a namespace, that's horrible. So we have a thing called V then, which would be similar in our init. Yeah. V gets in by 2 reshape 0. Okay. So then it becomes a PV gets interact. PV. Positions, directions, positions. Yep. V plus gets the new force and velocity. Oh, sorry, that's velocity gets added to by the force, and the positions added to by the velocities. And then you return PV again. Ba-ba-bum. Exactly. Yeah. Don't like this. 371353. Nothing's moving. Why nothing moving? The distances are large, the force is very small. But since it's GMM on R squared, we can put the scaling factor up by a lot for now. So we actually get some distance. And there we go. That's clearly not great. They're all... Oh! I need to normalize or somehow set the... Well, two things. One is the draw function is supposed to clear... gets... Yeah, that's not a great way anyway. I'll refactor this later. M.clear rect. No, 500. Can't make that on. No? So I want the dev tools, I guess. No, 500. Okay. What do you say? Syntax error. Invalid token. Well, that was probably the thing I just sent. Why doesn't it like that? Do. Execute JavaScript m.clear rect 0.500. Oh, this is wrong? Oh, why does it still have that? Oh. It doesn't like these. Oh, have I got... It doesn't like these numbers. No? What's unexpected? Negative. Whoa. Okay, probably want a quad DL in there, huh? Uh-huh. Hasn't drawn nothing. Yeah, and it's all stuck. In the left. Hello from Melbourne, programming Siri. Cool, what's up? I'm doing a little simple particle sim in APL. Basically, someone in the APL Orchard recently was asking about... Well, they'd related life... to be fair, I haven't watched the haven't watched the whole video, but there's this JavaScript noodle of how to simulate life. It starts with a particle sim, and so I'm doing the same thing. I have this much HTML and JavaScript to render squares on a HTML canvas, and then I have a few functions, to do the computation, initialize some particles, and stick them on the canvas. The bug I've reached now is that the way I'm computing the relative positions is has them all relative to the top left corner, which is the 0, 0 position, rather than relative to themselves. So there's 10 particles. I don't know why this doesn't draw them. It should. Yeah, but why it's missing that when I run it will have to be investigated. So every step, let's go in, we compute stuff. So we have positions and velocities. At the minute, start with everything static. Gravitational constant is just a scaling factor. Really what you're supposed to do is, for maximum precision, you compute all the interactions on a scale between 0 and 1, and then when you go to draw it, you just scale it up based on what the canvas is. But I'm being lazy, so I'm just doing this. Cool, thanks very much. Yeah, luck is what I need, because I'm flailing it a bit. Thought I'd be done by now, but you know. I got most of the stuff there. So what's the issue? These are the relative position, the relative distances between every particle and every other particle. D are right. D is just yep. All right, cool. Distances. R gets like so yeah, S is relative positions. R is relative distances. Directions are the relative positions. Cicera. You love to see it. It's probably because I'm using an HTML renderer with Ride. Did I get an Apple core? Yep. So I can send that to help later to support. But what we got to do now is kill that and start again. What was I doing? I was editing a function while I had an HTML renderer open. That's as far as I know. A-life. We're going to create comma. Conflicting file names. Well, okay, let's clear this. Let's clean up my structure a little bit. I'll get back to it. Depth is an operator. Don't really care for you. Don't need you. Don't need you. I'm gonna do some refactoring like later. Have a think about it. For now, I'm gonna pull everything out. Don't need you. Don't need. Oh, you're still open. Taking some inspiration, but don't need that anymore. Okay, let's go for it. Yep. 10 particles. I mean, what happens? What if I quad DL a tiny bit? Oh. Something sus is going on. Something sus that I can't what are we on? 23rd. Okay. A life create hash. Doesn't do it. Okay. Good lord. Directions are the relative displacements divided by those distances. Yep. Force. Yeah, okay, that's problematic now. We have to sum these distances. And the problem is S is like this, two-dimensional. You're very new to APL. That's alright. The problem I have isn't necessarily with the expressing an APL. It's me trying to wrap my head around. I need to just stop and think a bit more slowly, really. What I have is a collection of particles whose positions are these. So every row here is where they live. I can show you that on the canvas. Right, so it's all of these dots. Then I get the relative relative displacements from one particle. So this matrix here is for one of these particles and all, well, 10 particles. So it's 0 displacement from itself, and these are all the relative displacements. So then, in order to get the direction that the force, the overall force, will apply in, I think I have to sum every matrix, because each matrix represents a particle, and then divide this by and hold on, getting closer. Relative distance to every particle. The force is inverse proportional to the distance, not the displacement, and we can compute that. That's not a problem. But it's then the direction Oh, right, okay. No, the directions have to be kept independent. So the direction for every force, because there are 10 by 10, 100 forces, although obviously some are mutual, so it's sort of half of that, depending on your perspective. Take the first one. And if you take the sum of the force times, well, the sum of the force, we're just getting rid of half the forces by basically our force is a big grid. Right. Which is the force between every particle and every other particle. And then we take this outer product here. There are cheaper ways to compute this, but this is just the simplest way. As a mask of the lower left triangle, so we only get half the forces. We add those up, and this is the net force on each of our 10 particles. Problematically, you can't. Oh, well, this will be a column-wise sum then. Okay, there we go. Yeah. If I'm gonna get rid of, depending on which triangle I get rid of, depends on, determines, does it? Whether I do a column or a row-wise sum. No, I'm still missing one. So I'm not doing this bit right either. Fantastic. Or is it just half the sum across or down? Because what I'm worried about is I'm double counting. Now, for the sake of the simulation, it doesn't really matter. .0349 up there. Wait. Oh yeah. Or am I not double counting? This particle feels all these forces. This particle... No, okay, it's just the sum. It's just the sum across, I think. These are the magnitudes of the forces. Of the directions is the bit where I'm having a bit of a mare. Being a bit daft. You have the displacements. This would be a much more interesting stream if I'd done all of this ahead of time, understood it fully, and then came and just explained everything. But for now, you can just watch me struggling. So I'll do that for just another little minute. I might start a new stream on some other tools where I actually did do that. This was kind of a tempting distraction. Right. So this row will have the direction. Yeah, you multiply the force magnitude by the displacement. Yeah, but do I need to normalize the displacement first? That's my question. Shape S is this. Shape mag S is this. So divide by rank every matrix by every row. Oh, and then it needs a further rank, I think. Every matrix, every row, every vector. Huh? Something like this. Yeah, and the shape of each of those is 10. And when you do it on a matrix, you are dividing every row by every scalar. And that's the innermost loop. Is that all you actually need? Doubt this is going to work. Does it give it the results? Yeah, looks like it. Well, you know, when it works, it works. Right. So like this, divide rank 1 not. Every row in S divided by every scalar in the magnitudes of S gives us the norm, gives us the directions, and then you take the magnitudes of forces, if I can compute them. Yeah, doesn't actually matter which way. I sum these and times them by the displacement. Oh, sorry, directions. S is the displacement because I'm using physics conventions for the names like an idiot. These are magnitudes of forces. So it's a similar thing. You're taking every scalar here and every vector here. Probably the displacement times. Yep. No, just the forces. Right. So now for these are forces with directions for each of our 10 particles, and I think you just want to sum each matrix to get the resultant force on each particle, which is this guy. Okay, so to gravitational constant for scaling, magnitude, absolute magnitude of a vector, magnitude of Euclidean vector. These are the relative displacements. These are relative directions. These are relative distances. These are magnitudes of forces between particles. We needed R anyway, that's what this is. Force on each particle. Velocity increased by the force because acceleration mass 1 for now. Particles increased by positions moved by velocity for a step. And it's not a very good So why that one has fallen right off, I'm slightly interested in. Nice. It's definitely closer. I think there's probably some numeric, uh, some precision errors that are probably causing things to fly off. Whoa. But everything is gravitationally attracting. Look at that. All right, thanks very much for the help in the comments. I've done. This is the sort of hack it and see technique of programming, as you can see. But I guess more to the let's sort of conclude this by getting to the point of the stream, which was Connor asking about minimal artificial life. It's not finished. I think I'll continue this in my own time, and then I'll come back, having already done it once, and then being able to just do a stream that's just explaining how this works. So that'll either be Monday morning or a week today. And it's the question is how elegantly can this be implemented in APL? And that's very much up for debate, but let's take a look. So I think this is about as far as we get. So the main difference is, other than the fact that I've massively stripped everything down, and again, when I come back to this and do another stream about it, I think it's going to have more of the features here, and I'll figure out how to structure it to be all nice. This is all just very much his functions passed to functions. Maybe we'll do it that way. Maybe I won't. But what we're going to compare is really this interaction code. Everything else is much of a muchness, like my JavaScript. This is everything I'm using to draw, which is stolen from there, but it's not very much. And everything else, what have we got? An init function to just create the renderer that we can interact with. But if I wanted to do it in a web browser, I'd probably use Jarvis. But this rule part, which I've called interact, this is the main difference. And you can see it's not that many fewer lines, I'd say. And conceptually, I've clearly had a little bit of a wobble getting some parts of this together. But we'll chalk that up to lack of preparation. The main difference is the sort of the APL difference, right? In the JavaScript version, there's a nested loop that sort of says between every particle here and every particle here, let's go deep within that loop and let's and then look at every particle interaction on an individual basis and compute everything inside the nest of the loop. In the APL version, what you do is you compute each aspect of the interaction for every particle and every other particle all at once. Right, so without some kind of parallelization compilation techniques or whatever, without a compiler doing it, because this is interpreted code, you get this sort of parallel set of computations. So the relative displacements are all particles, what's the displacement to all the other particles, and then let's compute the magnitudes of all of those in one go. It's really, so it's just very rank polymorphic. The most pleasant surprise was definitely, and the thing that threw me off the most, was trying to do this, the high rank way. All right, using the rank operator to do a high rank outer product. So this matrix of positions becomes a 3-dimensional array of matrices, and just being able to do the division between each row of that 3D array and every element in a matrix was pretty neat. So this is probably actually -2, rank -2 to generalize it, I think. I don't know if I'd be that happy expressing it that way. And same here. Like, I know it's kind of, that's what that aspect of the rank operator is for. But clearly I didn't think of it that way. Anyway, so just the last thing, let's take our 10 particles, let's run 1,000 steps, but we'll increase that, I think. Just take a look. So maybe the scaling factor's too high, like they get too much velocity. Ooh. Far are we? Oh. The scaling factor's too high. So yeah, they interact too heavily. So just need to set G to be something less. Whoa. Okay, yeah. So you can see the when they get really close, the force gets massive, and they just ping off each other. When I did the proper thing, I can't remember how I mitigated for that. Anyway, yeah, judge however you like. Let's take a look at the code. That's more again, and then I'll call it. Okay. And I'll also pop this on GitHub and deal with all that later. Gravitational constant. It's just a scaling factor. Prevent division errors. This is the positions and the velocities. Alright, yeah, that'll do for now. I'm going to sign off and go do some other bits. So, yeah, thanks to the couple of you who commented, people who may have popped in for a moment and seen what's going on. I don't know how often I'm going to do streams like this, but I thought it'd be a laugh. Hopefully this was mildly amusing to you. Talk to you later. Bye.